Okay.
So I guess like today we mostly are going to talk about math in relation to philosophy. Let's start from defining math. Like, do you have some working definition for math?
Yeah, that's a good question. Math is kind of like anything where you have like a really rigid set of rules. Um, yeah, so I guess, I mean, when people think of math, so I would say most people, when they think of math, they think of numbers, but
Mhm.
math doesn't have to be numbers, right? It could be geometry, but it doesn't even have to be that.
Just any symbols.
Symbols that you manipulate according to rules, I guess. So
Mhm.
it's, um, I mean, I feel like languages, like the English language is 26 letters, but I wouldn't say the English language is math. I would say grammar is kind of like math because grammar is
Mhm.
like the rules for how you put the words together, right? So that's kind of mathematical in a way.
Yeah, but
Um,
in math, there it's rigorous, and in grammar you may
break the
basically,
rules.
yeah, you don't break rules, but you may, there are some exceptions and some rules, and there's no unified theory of grammar which everybody agrees on and says this is how it works, and there are so many different rules. Whereas in math, if there's a certain rule, all mathematicians say, yeah, this is how it works. So you can say, no, I haven't another different math.
Yeah, so it doesn't matter what the symbols themselves are. It's the relationship between the symbols. So
Mhm.
like we write the numbers as 1, 2, 3, 4, but we could have written them as something else, right?
Yeah,
It could have been
just
squiggle. It's
Chinese
not,
Chinese characters. Yeah.
yeah. It's not the way the symbols look, it's how they link to each other, or it's what you're allowed to do with them, I guess. I guess that's math, or that's one definition.
Mhm. In Wikipedia, they say there's no like accepted definition, but they give three types of definitions. Like one of them is logist, logi,
Logistical,
logicist.
logicist.
Yeah,
Yeah.
another intuitionist, and the last one formalist. And I guess what you described is more of yeah, it's kind of formalist one. So science, well, like symbols, rules for operating on them.
Yeah, that's the way I kind of think about it.
Yeah, and for logicists, that's the science that draws necessary conclusions.
Hmm.
All and for Bertrand Russell, for example, it's like all mathematics is symbolic logic.
Yeah, you can reduce it to logic, most
Mhm.
things. Set theory, it uses logic. I don't know if you can just say it is logic. Yeah. Um, but yeah, math and logic are very interrelated,
Do you think it's
definitely.
possible to kind of create unified theory, like this one, which was in this video by Wes Cecil and Bertrand Russell, like
Yeah.
when he talked how Bertrand Russell tried to find kind of rigorous math for philosophy, and finally he failed and dropped all of that and said, okay, now let's do something else.
Yeah, maybe he just got bored with it because yeah, if you
Mhm.
just keep looking at the same thing over and over, eventually your brain kind of just gets tired, right? And if you feel like you're not making progress, then you kind of say, "Hey, let me try something new." But yeah,
Yeah, I guess progress is the key here. Like if you're doing something, it just gets better and you feel it and keeps you doing that. But as soon as you stop, as soon as there's no way to get forward,
then you move on.
yeah, I
Yeah,
give
what's
up.
what's really interesting is the risk taken by either mathematicians or logicists when they're solving a really hard problem, because it could happen that they spend 20 years on it and they still can't get anywhere, right?
Mhm.
So there's a
Yeah.
big risk. Like it could have been like you saw the video with Andrew Wiles. It could have been that he couldn't figure it out, or that he just didn't get very far, and then he's just stuck. And I mean, look at all the years that he would have invested in that, right? So there's and I feel like this happens a lot too in academia. Like when people choose topics for their PhDs, a lot of times they won't really choose the problem that they want to solve because they're afraid 4 years are going to go by and they won't get anywhere, right? And then they won't have a PhD.
Mm-hmm.
So there's a lot of risk involved in it.
Yeah, but this guy Andrew Wiles, he believed that he knows how to solve the problem. As soon as there were other guys who worked on some geometrical, like I don't remember the names, but there were two other guys, Chinese.
Taniyama Shimura.
Yeah, and then when they found the solution to another problem, he realized now, like I can prove it. It just takes a certain amount of time.
No, I don't think so. No, like once he knew they.
Mm-hmm.
No, he was definitely not certain that he could do it. Like even once those two Chinese guys, Taniyama Shimura, discovered their theory, that was not guaranteed at all that he would solve the problem. In fact, a lot of other mathematicians that knew the same thing, and yeah, they just couldn't get very far with it. So it's a big risk. Like he could have just spent all those years and it just wouldn't have gotten very far. But yeah.
Mm-hmm. But I guess if he wouldn't believe that he was able to solve it, he wouldn't do anything.
Well, he thought there was a chance, but he wasn't certain. He thought he just knew there was a probability he might do it, but maybe it was like only a 1 in 20 chance, or a 1 in, you know what I mean?
Mm-hmm. So he started like, okay, let's try it. Probably it makes sense. We'll figure that out. But then, yeah. So I guess the more progress he made, the better he like saw how to really solve the problem.
But you remember when he presented the proof to everybody and everybody thought it was right, and then you remember the guy that found the error in it. You remember that part?
Yeah, the next year he basically was he said he didn't enjoy working on the same problem.
And not only did he not enjoy it, he wasn't sure if his way of doing it could actually solve it. He was about to give up, pretty much. Yeah. He was very close to giving up. Yeah. So
but there's finally he figured out.
Yeah. So there's like a lot of risk in it. It's far from a guarantee, but yeah.
Yeah, do you think it's like this? This guy was working on the problem for 7 years, right? And he didn't tell anybody that what he was doing.
I think he told his wife, but yeah, I don't think he told anyone else.
I don't.
But the thing is,
so
I don't think he told people he was working on that specific problem. But I think they knew that he worked in an area of math that was like related to it, right? Mm-hmm. So I think like, but he didn't tell them he was working on that one specific thing.
Yeah, but the point he couldn't discuss it with anybody. He worked on it alone, and
right.
For 7 years, is basically going in isolation and focusing on one thing.
And I wonder why he worked alone. I think part of the reason might be that if he told people he was working on it, they might laugh at him, or they might say, "Oh, there's no way you're going to figure that out." Mm-hmm. So I feel like maybe that's part of the reason why he didn't tell people. Not so much that he wanted to get credit for it himself, but that he would be embarrassed. Like other people would say, "Oh, you're not going to be able to do that," right?
Do you think that you are able to do something like that, like to work for several years on a particular thing without telling anybody that you are doing?
I think it's possible. Yeah.
Yeah.
I think he did that. Yeah.
The thing which came to my mind, it was like studying language, like Chinese, for example, without saying anybody, and then suddenly you appear to speak Chinese, like perfect Chinese.
Oh yeah.
Very well.
But math is different because the thing is, even after he figured it out, like there's very few people in the world that could understand it at that time, right?
Yeah, I see.
So even if he told people, only a few would be able to actually know what it meant, right?
It took some time to read this course of lectures to make them.
Yeah, do you remember when he was giving the lectures and then everyone dropped out of the course? Everyone left the course except for that one person?
Yeah, since he told that one person what lectures were about. And
Yeah, the other people were just confused. Yeah.
they couldn't understand what was going on.
Yeah. But yeah, just that feeling of working in isolation. Like, I wonder what, yeah, I think I know why he did it. Like I said, that's my guess. I'm not positive that's why he chose to work in isolation. But yeah, just the psychological, like, yeah, just the isolation. I feel like it's not really a good feeling being all by yourself. You know what I mean?
Yeah, but still, when you are, for example, doing something like math, there's generally very few people who can understand you. Your circle of social circle is very limited. You can't talk to average people about some deep mathematical problems, since what's going on at school. People basically hate studying math, and when you start thinking about it, as soon as you start thinking about it, you go deeper and deeper, and finally, like in a couple of years, there's just in I guess if you consider your close environment and nobody studies math, whether you talk to your friends and relatives, they still don't understand you, so you just lose the the whatever make communication meaningful. Since for you, like if you are working hard on certain problems, it's the thing we should like to discuss. But if you start talking to somebody else and they just distract you with their stuff, like talking about whatever is going on, about some weather or food or work or any stuff like that, basically you can't really connect with them. So math itself is a form of social isolation with close circle of people who can.
That's kind of why I decided not to go to grad school for a PhD, but I do my YouTube channel because it's the level of the math, it's advanced, but it's not, there's still like worldwide, there's still a lot of people that, like, maybe, I don't know, in the US maybe there's like 1,000 people that could understand that, right? So it's not, there's still enough people that you can talk about it with.
Yeah, but at the same time, if you like go to PhD, there's a group of people with whom you like, if you do this work,
your classmates.
Yeah, basically you have 1 to 5 people, but since you are doing the same thing, it's like the quality of communication will grow, and you'll know exactly what you're talking about, and it's going, instead of having many like conversations with people about useless things, you have conversations with few people, but you can perfectly understand each other.
Yeah, it kind of strengthens the connection between them, because since like there's only a couple people that can know it, it's like you have to go through them to discuss your ideas, so it kind of strengthens the bond between you.
Right? You can discuss these ideas only with them. There's nobody else who can. I guess I had similar experience in playing video games when I was like in my 20s. So there were a few games which I and maybe like five other people were playing, and I couldn't talk about it with anybody else. But when I start talking about these games with those people, it's basically like you may talk for 5 hours, for as much time as argue about some different characters, what's going on, some different strategies, tactics, etc.
Yeah, so that's like a similar experience when you play video games.
Yeah, sure. Okay, so I have some, some general questions related to math, and I have some personal questions.
Yeah.
So which one would we like to start with?
Like general... You can start with the math ones and then go to the personal ones. I think that's...
Oh, okay. So let's discuss some basic concepts in math. Like, what are, in your opinion, these concepts?
Basic concepts.
Yeah, or key concepts which you need to understand math and.
I mean, I guess, right,
Yeah,
it starts
yeah, it's
out.
like you may talk about just since you're like working on geometry, you may also
Mhm.
like you may start from geometry and define some key
Yeah,
concepts.
so one interesting thing is in geometry, most people know like a triangle, right? So there's three vertices and three
Mhm,
sides, right? But so then the question is, what's the center of the triangle?
mhm,
And what do we mean by center? And it turns out that there's like thousands of different ways to define the center of a triangle. So that's, in fact, there's a database online. It has like, I think it's grown to like 80,000 different ways to define the center of a triangle, right?
80,000.
Yeah.
Mhm,
So the most common way that we think of, so there's a few that we learn in high school. So one is the circumcenter. So the circumcenter is basically if you draw a circle around the triangle so that it just goes around the
mhm,
three vertices.
mhm,
So like you draw a circle so that the triangle is inscribed in it. Like it just touches the three vertices, right?
mhm. And
Then
then
this
the middle of the circle is the middle of the triangle, right?
exactly. So
Mhm,
that's one definition of, so that's called the circumcenter.
mhm,
Um, then there's a couple other different definitions. There's also the incenter. So like before I said you draw the circle going around the triangle,
mhm.
then you could draw a circle inside of the
Oh, okay, yeah,
triangles
yeah, I see.
so that it just touches the three sides. And the center of that circle is called the incenter of the triangle. Um, and then there's
And
others, there's the
it's just,
orthocenter,
it's
or
just
what?
yeah, it's just two, right? And there's like 79,998 more.
Other ways to do it.
Yeah,
Yeah.
wow.
And these centers have really interesting connections with one another. So yeah, I would say when it comes to understanding the triangle, first knowing the centers, the different ways to define the centers is like the first step. There's another way too. I'll just mention a third way just for the heck of it. But if you have a triangle, if you take the midpoint of each of a side, so if you
Mhm,
connect the vertex to the midpoint of the opposite side, and then you
mhm.
do it the same for the others, those three lines meet at a point,
Yeah, they
and that's
intersect.
called
Mhm,
the centroid.
mhm,
So that's another center of the triangle. So yeah, basically there's many different triangle centers. And then there's a couple other important concepts. There's so two lines, if they're not parallel, then they meet at one point.
mhm.
But three lines don't necessarily meet at a point. Three lines might not meet at a point. So when they do, that's like special. That's called concurrent, right? The three lines concur at a single point.
At the single point. Okay, like
Yeah, so
so there's
two
two.
lines
Mhm. So
pass through a
they either parallel or they meet somewhere,
right,
right?
or
But
they meet somewhere.
the third line,
If it
it has
passes through,
it has the same point with these two lines.
right. If it has the same point, then we say it's concurrent with those
But
lines.
how it relates to triangle?
Oh, no, it's kind of a
Yeah.
separate concept.
Oh, okay.
Yeah,
Okay. Sorry.
yeah.
Yeah.
Um, so yeah, that's one concept in geometry. But the triangles, here's another really interesting, here's one of my favorite properties of a triangle, and it's not that easy. So I'll just kind of simplify it a little bit
Mhm,
for now. But if you have a triangle, you take the midpoints of each of the three sides. Maybe I could draw this on a paper.
mhm. Okay.
So but if you have a triangle and you take the midpoints of each of the three sides,
Mhm,
and then also let's say you take each of the vertex and you draw perpendicular to the opposite side. So you get 6 points, right? So you have the 3 midpoints, 1, 2, 3. And then you also have a perpendicular, perpendicular, perpendicular from each point. So that gives you 6 points, right? Those 6 points, it happens that they all lie on a circle. So that's a fact that I feel like is not super obvious, right? That's a fact that you'd have to think about, like, why is that true? And it's not easy. It takes a while to show. But let me draw it on a paper. Hold on just 1 second.
Yeah, okay.
Yeah, I can put it on the screen. Okay, so I start with a triangle. Can you see the 3 midpoints?
Yeah.
And then I'm going to add 3 more points. So you see what I did here is I drew perpendicular lines. So I took this point here and I drew it perpendicular. So at a right angle. And then I drew this point and I drew it perpendicular, right? And then I took this point and I drew it perpendicular, right? So the 3 perpendiculars, and that gives us 6 points, right?
Yeah, and they are like in each point in the middle of this part, like this. So we basically divide one side in 2 parts, and these points they become half of the set of this, this part of these parts. Okay.
And then so I have 6 points, right? And these 6 points, it turns out that they all lie on a circle. So yeah, I have 1, 2, 3, 4, 5, 6, right?
So you may draw a circle
through them.
And there's center of the triangle, another center of the triangle.
Another center, yeah. This is different from all the other centers I told you about. So it's not very obvious. I mean, usually when you have 6 points, there's not always a circle that goes through them, right? But for these 6 points, they have the special property that there's a circle that goes through them. And the center of that circle is another center. And also what's interesting is, like I said, three lines don't always meet at a point, right? But in this case, these 3 lines, 1, 2, 3, they will always meet at a point. It's not that obvious, but it's true. And that point is another center of the triangle. So, and where it gets really interesting,
so it's going to be all for every triangle, right?
For every triangle, yeah. And what's interesting is, this is the last thing I'll say, just because I don't want to overwhelm, like, I know I'm saying a lot here. So I have, here's one center of the triangle, right? And these 3 lines will always meet at a point. So I guess this goes to kind of what I said about concurrence, right? 3 lines, they don't always meet at a point, but sometimes they do, right? So in this case, here's one center of the triangle. Here's another center of it. It's the center of this circle. And then here's another center of the triangle, which is the center of this big circle, right?
But
and
where is it? Wait.
Oh, it's this point right here.
Oh, okay.
It's the center of this bigger circle, right? And it turns out that this point is actually the midpoint of the segment between these two. So it's halfway between. So it's exactly halfway between the other 2 points. Which, so yeah, there's in geometry, there's all these sort of connections that you find, and it's not clear right when you see them why
so
they're.
I'm on 80,000 centers. So there's some connections, and you may always, if you know how to find them, you may basically find similar connections. Right?
Exactly.
So,
yeah.
There's like how many types of them? They're basically infinite, right? So that's one center may be connected to like hundred other centers, and like 80,000 like points.
Yeah.
Multiplied
They're all
by,
interconnected. Yeah, exactly. So yeah, it's not, so that kind of a math, there's very few like professors that do that kind of math. But I kind of just do it for fun.
Is it some sort of pure math?
It's pure math, yeah.
Just some exercise for
your brain. Yeah, there's very few applications of it.
Yeah, maybe there will be a found in the future, right? So like in math in general, we see that some pure math becomes gets applied in the future, and there's always like for any knowledge discovered in math, we'll find some practical applications, maybe which are not obvious now, but some new technologies may basically provide.
Yeah, so for me, that would be very fun if in the future they found applications for that.
Yeah, maybe we'll build some, spaceships, and they will look like triangles, and to support to make some gravity, or to make them work. Basically, you'll have to know all these points and put something there.
But yeah, so you asked me what are some key concepts in math. So that's geometry specifically, but you can generally break up math, or mathematicians have generally broken it up into a couple of different fields. So geometry is the study of space, kind of. It could be 2 dimensions, it could be 3 dimensions or more. Then there's also number theory. Number theory studies like prime numbers. So mathematicians have been obsessed with prime numbers forever. Certain, how frequently do they occur? What happens when you get to like 10 billion or like really, really big numbers? Can you try to predict where the next prime number is, or how frequent it's going to be?
Yeah, I've read, probably you've heard that guy, Neil Stevenson.
Stevenson?
Neil Stevenson.
I think I've heard of him.
He has a book called Cryptonomicon.
Cryptonomicon.
Yeah, it's like a huge, like more than 1,000 pages book, and I've read it 2 years ago. And there's this prime numbers, these ideas, and it's very fascinating, I would say.
Yeah.
Prime numbers basically used in cryptology to
for computer security and stuff like that. Yeah. So the guy whose video I sent you, Andrew Wiles, he studied number theory. But the thing is, it kind of starts out, so it kind of depends what kind of number theorist you are. So some of them study prime numbers a lot, and but others kind of study different things. So it's a little bit hard to explain, but what they'll do is, so there's the numbers we're used to, like 1, 2, 3, 4, 5, but then there's these more abstract kind of numbers. So you could say a number is like anything where you can add it, multiply it, divide it. So what they'll do is, like for example, imaginary numbers, right? Like I could take, I don't know if you know, like I is the square root of -1, right? So like that's like a different kind of number in a way, right? But it still works. It's still like sometimes we say real numbers are real and imaginary numbers aren't actually real. But in reality, imaginary numbers are no less real than normal numbers. Imaginary numbers, they're a consistent philosophy, right? Like everything you do with imaginary numbers, it'll never contradict itself. It'll always make sense, right?
Mhm.
You can multiply imaginary numbers, you can add them, it'll have all the same ways of doing it as with normal numbers, right?
Mhm.
So a lot of times mathematicians, they'll extend it to like new kinds of numbers. Like imaginary numbers is one example. There's these things called cyclotomic fields, other different kinds of numbers, but you could still add them in a similar way, right? So there's number theory. Then there is combinatorics is another kind of math. So combinatorics is where you like count the number of ways to do something. So like how many different times would you have to play the lottery to be sure you could win it?
Mhm.
So that, or like let's say you're sitting 10 people around the table and you want to seat them so that you don't have more than 2 men in a row. How many different
Mhm.
ways are there to do that? So it's like counting the number of combinations, right?
Yeah, I remember watching Vsauce. You know how I watched Vsauce?
I don't think so. I don't think I've seen it.
So there's 52 factorial. And
Mhm.
there's an example how big is this 52 factorial, and it's just crazy. You might just look at it on YouTube, and there's some great analogies. By, like, you know, if you take one drop of water from ocean and go around the ocean, sounds like go around the Earth and take another drop of water from the ocean, go around the Earth and take another, and then you know go almost infinitely, unless you take the entire ocean and then you go back and then you go forth and then you go back and then it's just some very I would say vivid examples, and
Mhm.
it still doesn't it doesn't get the like this 52 factorial is basically just more than it's big, it's the number bigger than the amount of atoms in the universe,
In the universe, yeah. So
and it's a pack of cards. So
yeah.
the whole point is how many different combinations you may get with a pack of cards.
Yeah,
And
so if you start with something just like a pack of cards, the number of combinations is already more than the number of atoms in the universe, right?
yeah,
Yeah.
and from the beginning, like I guess for all the time people played cards, we just got through very tiny part of all possible combinations, even though like people were playing it for thousands of years
For
probably.
thousands of years.
Yeah.
So yeah, that is a perfect example of combinatorics. I guess that there's other interesting questions. Like let's say you have an 8x8 chessboard and you want to say how many ways can I tile it with dominoes, right? So if I
Mhm.
have 2x1 dominoes and I try to tile up the whole thing, how many different ways are there to do that? Or like questions on like if I have a chessboard and I want to put the rooks on it so that none of them are in the same row or column, how many
Mhm.
ways are there to do that? So
Mhm.
anything that's counting the number of ways to do something is combinatorics.
Mhm.
So there's geometry, which there's number theory,
Mhm.
which is like prime numbers, stuff like that. Then there's combinatorics, which is like counting the number of ways to do something. There's a few other like branches, but I figure it's not worth spending all the time just talking about that.
Mhm. Tell me about this Euclid's geometry and non-Euclid's geometry. Like,
Euclidean and non-Euclidean. Yeah.
yeah, it's
So
I remember, just a brief introduction. I remember I found this on the internet for
mhm.
about 2010 or 2011, and I was really excited, and I started questioning why did I learn why I didn't learn these things at school. since at school we all just learn geometry, and well, this is so puzzling. Like we all were told about Euclid and about stuff, but it seems that this non-Euclidean geometry, it's revolutionized the entire field of geometry. And
so it's really interesting. So originally, so like there was Euclidean geometry, right? And in Euclidean geometry, like you can have parallel lines. Like if you have a line and you have a point that's not on the line, there's like one parallel line that goes through that point. So like,
and
there's
only
not
one,
two,
right?
there's only one. Yeah, there's always just one. So you'll never have two parallel lines going through that point, or you'll never have no parallel lines going through that point, right? So they started looking at, so that's like, so one of Euclid's axioms, like, so Euclid tried to take all of geometry and try to boil it down to like, I think it's like 5 different axioms, right? And one of his axioms is basically equivalent to that. It was basically the same thing as that. And they said that one seems kind of weird. That's like a kind of a more complicated one than the other 4. So they said, can we prove that one using the other 4, right? And people try to do that for a very long time. They try to take that 5th axiom and see if they could prove it using the other 4. And if they could, then they could kind of remove it as an axiom, right? And they could just say that there's only 4 axioms, right? And people tried for a really long time, they couldn't do it. And then they realized that they couldn't do it because it's not actually possible to prove it. And they knew that they couldn't prove it because they could come up with another kind of geometry where the 4 of them held, but the 5th one didn't. So if you can come up with a kind of geometry where the 4 axioms hold, but the 5th one does not, then that means you cannot prove that 5th one using the other 4, right? Because it could be that it just doesn't hold. Does that make sense? And what's really, so originally they're like, okay, so we came up with this really weird kind of geometry where 4 of them work, but the 5th one doesn't, right? But then they're like, does this really have any real world application? Or is this just some fancy thing we made up in our minds, right? Some intellectual exercise. And then when Einstein came around, we learned that actually is how the universe works. So we came up with this thing, kind of like you said, we came up with this thing as like an intellectual exercise, right? And we thought it was just some weird, interesting thing. But then we realized that actually is the way the universe works, not the way we thought before. So then the question is, well, then why don't we learn it in school, right? The thing is
it too complicated?
So first of all, it's more complicated, yes. But second of all, on Earth, the gravity is pretty strong. So on Earth, it's very close to Euclidean geometry. So even though it's technically non-Euclidean, it's a non-Euclidean that's very, very close to being Euclidean, right? So the theorems that you learn in school, for most purposes, they're good enough. They're accurate enough for making a shirt or making a table, right? We would never need to be that precise, right? Or we would need the non-Euclidean.
Yeah, depends on what exactly are you trying to do.
But if you're an astronaut, or if you're making a GPS, let's say, then you would want the non-Euclidean. So you'd want to know the Einstein's theory, right?
And again, if Einstein's theory and non-Euclidean geometry is like more true than Euclidean one, like, well, how, like you can't just if you know that you can't forget about it, and still like you see that you have to use say Euclidean geometry in daily life, but still if you
Yeah.
know that it's kind of it's not actually, it's not right, you still, okay, it's self-deception, or it's very hard to accept Euclidean geometry after you know that there's non-Euclidean and it's actually much better for describing the universe and how it
It's
works.
it's it's more accurate, but it's more complicated, and it's only a little bit more
Mhm.
accurate for the reasons we use it.
But
So yeah.
what do you think about this problem that it's very hard to teach people at school math and geometry and basically algebra, arithmetics? Like why it's so hard? Is it because of like it's too abstract, or?
I think the real problem is that we don't have enough good teachers. So I think it's kind of like inertia. I think it's like you have a small number of people that know it really well and are really smart, and
Mhm,
they could teach it better. But most, I would say, like at least in the US, maybe around 95% of the math teachers, they know the formulas, but they don't
mhm,
really know why we came up with them or why the formulas work. So
mhm,
like most math teachers in the US, like they could tell you what the quadratic formula is, but they couldn't tell you a proof of it or why it's true or how we historically, how did we figure it out? You know what I mean?
mhm,
So I think it's just in one generation, there's not enough good teachers. And so in the next generation, there's not enough good teachers. And I think it just keeps continuing. Um, and and so I think what happens is, since when you don't have enough teachers that know it really well, they have to teach it in a very formulaic way. Like they have to say, here's the formula for this, here's the formula for this, just do it, don't question it, don't think outside the box, just do exactly as I tell you to do. And that's how they learn
Yeah,
it.
but you see, we may say the same about all sciences, right? There's
Yeah.
no good teachers who may teach other science, but still in school, like I wouldn't say that we learn physics or biology or chemistry better than math, but still, at least in my environment, like most people just hated math.
Hmm.
uh, about physics or biology, it's much less, it's at least there's something that most people can understand. So biology is life, there's some cells, everybody has a something to think about when we study biology or chemistry or whatever. But in math it seems like purely abstract. For on basics, like
Yeah.
this arithmetic, 1 + 1 = 2, it's okay. But as soon as there are some formulas, equations, and they're like they have no practical applications, especially for kids, it's very hard to follow, to remember all these kinds. So you basically, the point is you can't think about them unless you have a real interest. So if it's really interesting and you may think about it, you may write about it, you may study on your own. Yeah, you may get along without teachers.
Yeah.
But for many kids, it's basically it's it's very hard to follow, and very
It's just
I by myself, when I was a child, I remember
yeah.
when I was 5, I memorized the table of multiplication before school, and then I
See, that's so boring. See, but that like
yeah, but after I came to school,
yeah.
I liked math, maybe first couple of years, but after 6th or 7th grade, I started showing less and less interest, and finally I gave up. I just stopped.
Yeah.
No, I could grasp everything that teacher was saying, but I lost my interest, my passion for
For
that.
doing it.
It was too formal, and I saw no way how I can use it in my life.
I don't know if it's just the formality of it though, because there's a lot of things. I mean, there's a lot of things people do that they can't really use in life. Like let's say dancing. right? Like when you dance with someone, there's no application to that,
Yeah,
right?
but dance itself is like it makes you feel not exactly you, but generally it makes people feel good when they dance. But when they solve
I
math
feel good when
problem,
I do math.
yeah,
Yeah.
you can. I see.
Yeah.
I can too. But
Yeah.
most for most people, it seems to be very high. I think maybe it's our general kind of evolution. So maybe in few hundred years, in few thousand years, we all will evolve to the degree where generally everybody will understand math and be able to learn
But
math as we can learn language now, as we can learn.
I think it's more the way it's taught. So I think people could like math just the same way they like dance. I think the problem is that the way it's taught is very like rigid. Like so when I'll tell you how I learned math. I actually don't know if I learned any math from a teacher. The way I kind of learned math was so my brother was older than me. He had a textbook, right? I would just start opening it up to random pages, right? And I didn't know what any of it meant at first, but I would just flip around and then I would just pick up little bits and pieces. And then I would like try some problems. At first I would only get like 20% of them right, right? I didn't learn it in a structured way. Like I didn't learn it in a very rigid, do this formula, do this formula. I kind of hopped around and did it my own way, right? And I think that might be why I liked it more.
But you also learned it on your own, right? Nobody
on
forced
my
you
own.
like study this, study that, then study that. You just it was your will,
Yeah.
which
and I didn't start out super smart, right? I just started out flipping around. I tried a bunch of problems. I got most of them wrong. I just skipped here, there, but I was free, right? I felt more free, right? So like, I'm sorry.
Reminds me Pascal's story. You know, have you heard Blaise Pascal?
Blaise Pascal. I've heard of him. I know he did a lot of geometry and stuff like that.
Yeah, he also like his father was a mathematician, and he didn't teach him. He also discovered the book and started. It was a Euclid's geometry, by the way, and he discovered it in early age, I guess 6 or 7 or something around that. And he started reading it, and as a boy, he finally came up with some solutions and showed it to his father. And his father, wow, this is like, how did you do that? Cool. Like, tell me, I don't understand what you've done.
But I don't think you have to be like to appreciate math in the same way like you appreciate dancing or music or something like that. I don't think you have to be like naturally like a genius or super smart. I think most people math kind of makes them nervous because the education system, it's like you have to get good grades, right?
So there's some pressure, right? So,
there's pressure, yeah. So it's like you kind of have to, because the thing is like when it comes to getting into a good college or university, it's like every grade matters, right? So you have to pass this test, next test, you have to pass it. But I feel like to enjoy something, you need like wiggle room. Like you can't, like a math test, it's like you have to get 95%. Like if you want to get a good grade, you have to know almost all the questions. And if you don't, it's like you're not going to get into the college you want. And or you know what I mean? Whereas I feel like true learning it's like getting like 40% of it, or it's like just kind of picking up on bits and pieces. It's not like you have to like know everything on the test and like there's I feel like it's too rigid. But yeah,
it's not about like in this case what you say about the education. So there's a purpose, right? You want to get to the university, or you want to get a good grades. But when you study it for the sake of studying, and there's no purpose but just to do the stuff and see how you can do that to learn.
Exactly.
Yeah, it's different ways. The same as studying language, for example. I see that one of the problems most people have in studying languages, they just study them to get a good job, to, you know, to do something else, to travel. And this purpose is actually, on the one side, we may say that it motivates you, but on the other side, basically you have a kind of attitude towards language which doesn't allow you really grasp what's going on there. It's like having a girlfriend. So imagine that you like have a girlfriend and you tell her, you know, I need you to do X or I need you to do Y, right? So it wouldn't work. And the same with math or with any science. So if you do it for its own sake, it just opens its doors to you and you go further and further. But as soon as you use it for something, say, oh, I want to study math and I'm doing it because I want to get something. And then, well, you'll get somewhere, but still you won't be able to appreciate and understand.
I would say it's both a pressure, but it's also the fact that like there's very little tolerance for mistakes in school. Like we should have it in a way where you're allowed to make more mistakes, I feel like, and still do well in the class. So like for example, let's say you write an essay, right? Let's say I'm writing an essay in English class and I make a little mistake here, a little mistake here, a little mistake here, but I could still get like a good grade on the essay if the rest of it is, in other words, it's more about what is there rather than what's not there, right? So you can make a couple mistakes if you're writing an essay. Maybe you can misspell a word or something, but if you have a really like a lot of good ideas, you would still get a good grade on it, right? Whereas for math, it's kind of more about the mistakes. It's more like, oh, you forgot to add this or you forgot to do this, so you get it wrong. So it's less about your ideas in school and it's more about mistakes, if that makes sense. Yeah, it's not good. I don't like it, but yeah. Yeah.
Okay. Let's discuss how math affects our thinking.
Yeah.
Like,
how does math affect your thinking? Yeah, so I feel like once you learn math, especially I feel like statistics in a way, you can almost see it in everything. But like once you learn like, especially like statistics and like risk and probabilities and stuff like that, it kind of affects the way you see everything. So like let's say I think it might rain, but I'm not sure, and I want to decide if I want to bring an umbrella, right? So once you know risk, you can't help but think, maybe there's a 30% chance of rain. Should I bring my umbrella for a 30% chance? Well, it'll take me this much effort, and so screw it, I won't bring the umbrella. But if you didn't know about probabilities and risk, it would kind of just be more of a gut feeling, I guess. Like you wouldn't.
It's kind of it's like math is just it's not intuition, but it's kind of it's basically rational thinking, right? So you predict what's going to happen, and then you make right choices, right? So there's less probability to get the outcome which you don't like to get.
Yeah, and numbers really affect, I mean, so much of our thinking, like especially money, right? Like before we had numbers, I guess we would just trade things, right? Like I would have a fruit, you would have meat.
Yeah, but still would trade them, I have two fruits and you have one. Like there wasn't like one thing for one thing, right?
It wasn't always one thing for one thing, but they were usually small numbers, right? So, or you might say, I might see you have a bunch of fruits and I have 2 pieces of meat and we just trade, and I don't know the exact number of fruits you have. I just know it's a bunch of them, right? But now that we have numbers, everything's so like we can pin it down exactly how many. So it really enters into our thinking everywhere. it's just a much more like rational mindset, I guess, or way of thinking about
Do you
things.
think you may endlessly improve your thinking by studying math and developing whatever like capacity for understanding the world through these mathematical
Yeah.
lenses?
I don't
Or
think so. I think
there's some limits?
I think once you know a certain level of math, there's kind of, once you get any more advanced, it's not really very applicable to the world. So
Mm-hmm.
I think statistics and probability. So I actually think probability and statistics have more application than calculus. It's weird. And in schools, they emphasize calculus more, and
Mm-hmm.
they emphasize like statistics less. But I think probability and statistics has more application to our life. Um, so yeah, but I think once you get to a certain level, like Andrew Wiles, like his level no longer has any like connection to reality, at least
Mm-hmm.
as far as we know right now. But
Mm-hmm.
I don't think, yeah, I think you reach a point and then you're not really understanding the world much better after that.
Mm-hmm. I would say
Yeah.
it has no connection to reality, but still, like we see that maybe probably in the future, again, these ideas which he came across while proving this theorem, they may be they may be used, and there may be different realities, and maybe he just reached the edge of some intellectual whatever field, and the rest of humanity will just gradually crawl there, and at some moment, like everybody will understand, what's
Yeah.
going on. So you kind of well, that's actually what he's done, right? So like proving something which was unproved for 300 years or even more. So you have to get to the place where nobody else have been before, like has been before.
Yeah. So yeah, he's kind of in his own world. Yeah. I don't know, maybe in 1,000 years, like a lot of his ideas will start to apply to real life. I
Mm-hmm.
would think that would be really cool if that
Mm-hmm.
were the case.
Yeah, but you say like it doesn't make like you more effective in real life, but for him this is real life. You
That
see,
is
so
his
it's like
life.
it's
Yeah.
like I guess he doesn't probably care too much about what we call like reality, since for
Yeah.
him this is reality.
Yeah. It's really like math. It's really interesting how you can just get so into this one problem and be thinking
Mm-hmm.
about it all the time.
Mm-hmm.
Like I remember there's this one mathematician, he had a video on YouTube, like a TED talk, and he
Mm-hmm.
was talking about why he thought math was better than sex. And it's because like he said, sex, you can only think about it so long. Whereas a math problem, you can obsess about it like all the time. Like it can
Mm-hmm.
be like your whole existence.
Yeah, I think
Um,
it relates to every science.
yeah,
Uh,
but yeah, it's not just math, I'm sure. Like when Thomas Edison was like inventing the light bulb, like
mhm,
I think it was the same thing. He was always thinking about it, you know.
mhm.
Um, so yeah, I don't think any other animal besides the human has that capability to just focus on one very narrow thing.
Mhm.
I think humans are the only animal capable of that.
Another story uh, from my field, which I always was fascinated by, was this ancient Greek guy, Zeno, and his paradoxes. Like,
Zeno's paradoxes. Yeah.
yeah, Achilles and tortoise, the arrow, and I remember again it was around 2010, 2011 when I started actually using the internet and getting some knowledge, some information from there. Yeah, I've read like this paradox, and there was the idea that there was another guy, Democritus,
Mhm.
who actually like there was a argument between Zeno and Democritus, and Zeno basically it was the like before they invented calculus in infinite series in this I don't know how it's called, but yeah, before they already had something like that in Zeno's paradoxes, like when you basically go infinitely and you can't reach the
A finite number.
yeah,
Yeah.
you divide the ad infinitum basically the same line, but the more
Democritus.
Democritus said like there's atom and this is undivided. You can divide an atom actually means like like not divided.
Divisible.
Yeah,
Yeah.
and then like for yeah, I guess in the course of lectures which I watched, the professor said like it stopped the progress of math for 1,000 and for 1,500 years. Like this Democritus atom basically stopped the progress, and only in like with René Descartes and later with Leibniz, Newton, they were able to move it ahead.
That's so
Uh,
silly. So he just said that one thing that you can't divide
uh,
it anymore, and then it just stopped everything.
well,
Yeah.
it's kind of this idea that it was so influential, the atomic
Yeah.
theory in ancient Greece, that they stopped really thinking about Zeno's paradoxes. So they kind of, oh, we found the solution. There's the solution, and it wasn't just Democritus. There was, other people proposed solutions for his paradoxes.
Yeah. Interesting. I hadn't heard about that. Like I knew about his paradoxes and I knew that like they use calculus to explain it, but I didn't know that other piece of information that you mentioned.
Mm-hmm.
I'm sure you've probably heard about the different kinds of infinities, right? So like
Mm-hmm.
accountable infinity, uncountable.
Yeah, but it's just superficial. I watched videos about Hilbert's hotel.
Yeah, that's one
That's
example. Yeah. But
I
yeah, the
also watched
idea of
some courses later on. I guess Cantor was another guy who developed these ideas of different infinities.
yeah, and a lot of mathematicians were like very resistant to it at first. Like they were very like, this is silly or this
Yeah,
is
yeah,
wrong.
yeah.
Nowadays, most mathematicians accept it. Like the idea that you can have different sizes of infinity.
Yeah,
Um,
can I just tell you how I perceive it, like to see,
yeah.
so there's, for example, 1 and 10, right?
Mhm.
So we might say that between 0 and 1, there's an infinity.
Yeah.
So you may divide, and between 1 and 10, there's an infinity. And we may say
Yeah.
that for every point between 0 and 1, we may find the point between 0 and 10. So
Yeah.
we may say in that sense, they're equal.
Yeah.
But it's like, it's like
You can
this.
pair them up.
Yeah, and yeah, it's just mind-boggling. Since
Yeah.
like, how can that be? It's like we see that these lines, like one is one is bigger, another is smaller. But
Yeah, it's very simple. Like every number between 0 and 1, multiply it by 10, right? So if you take the numbers between 0 and 1, multiply it by 10, then you get 0 to 10.
yeah,
Divide it by 10, you get back to 0 to 1. So they're the
yeah,
same number, right? You
yeah,
can go back and forth,
yeah,
right?
yeah.
And what's interesting is there's more numbers between 0 and 1 than there are all the whole numbers. So like there's an infinite number of numbers between 0 and 1, right? And there's an infinite number of integers. So like 1, 2, 3, 4, 5 going on forever. But there's more in the sense that I mentioned some infinities are bigger than others. There's more numbers between 0 and 1 than there are integers in total, right? That's interesting in my opinion. Yeah.
And why? Like, can you just elaborate on this? Why there's more in?
Well, why are there more?
Yeah.
So I could give you so basically let's say I took each of the positive integers and I did 1 divided by it, right? So like a third, 1 over 4, 1 over 5, 1 over 6, going on, etc., etc. All those numbers are between 0 and 1, right? So basically, if I take all the whole numbers, like 1,000, like 1,000, and I do 1 over 1,000, that's a number in between 0 and 1, right?
Mhm.
So it's like you could take all those integers, and if you did
And
1 divided by them, they would all
Mhm.
fit in that space from 0 to 1. But then there would still be other numbers there too, between 0 and 1, right? So there's, I don't know if that makes sense.
Wait, but
But
in this case, they're like integers. There are more integers.
no, there's
No,
more numbers between 0 and 1 than there are all the integers.
still
Yeah,
can't get it.
it's all right. But basically, so one idea is, so when is one infinity bigger than another? So we say two infinities are the same size if you can pair them up. So I'll give you an example. Let's say we have all the integers,
Mhm.
and then we have all the even integers,
Mhm.
right?
Yeah, here I can see that one is bigger than the other.
No, they're the same size. This is what I'm going to prove to you. There's the same number of all of the integers as there are
Because you
even
have
integers.
okay now yeah I've mistaken like for one you have two, for two you have for two you have four, for three you have six, etc. And then for each number you have another number, right?
Exactly. You can pair them up. You can put them in
Mm-hmm.
pairs, right? So for
Mm-hmm.
one, you have two, for two, you have four, three, you have six, right?
Mm-hmm.
But the thing that I said, it's not that obvious, but it's true that there's more numbers between 0 and 1, like real numbers, than there
Mm-hmm.
are all of the integers. So like between 0 and 1, like 0.76 would be a number, right?
Oh,
Or
okay. So integers, you mean 1, 2, 3, 4, 5, but it does like one. For example, it's not fractal. What was? What's? Wait a second.
irrational.
Yeah, there's rational numbers, irrational numbers, and it's not integers, right?
Right.
And between
Oh, were
between
you thinking, I'm sorry, I should have mentioned that. Were you thinking it was just the two numbers, 0 and 1? Yeah. No, I mean
yeah,
all
no,
the
no, no,
numbers
no,
in
no, no, no,
between.
no. I thought that integers like 2, 3, 4, 5.
Yeah.
Between them, we may also use like 3/4 or any like pi or any other numbers, but it's just integers in like this line. So 1, 2, 3, 4, 5, 6, 7, etc. Right?
Yeah.
But between 0 and 1, there's
Mhm.
all sorts of numbers like real numbers and irrational numbers. So
Yeah, exactly.
that's why we can say that this infinity is bigger than the infinity of integers.
Yeah.
Okay, now I can see it.
So yeah, I feel like a lot of math, like sometimes I talk a lot about like the beauty of math, or how like interesting it is, but I feel like probably throughout my life, a lot of the reason why I've done math is just because it made me feel smart.
Mm-hmm.
I think when I was really young, a lot of my teachers would, like, they'd see I'm good at math and they'd be like, wow, you're really smart, and they'd put me in the next grade. And that's kind of, so I feel like there was like a little bit of an ego element in it,
Mm-hmm.
like a little bit of arrogance. Like
You can
it made me, or what?
boost your self-esteem, right? So
Boost my self-esteem.
mhm.
Yeah. And I feel like a lot of people get into their passions that way. Like a lot of people, they think they do it just because they enjoy it. But I feel like often if you trace it back to a very early age, I feel like often there is that sort of self-esteem element.
Mhm.
Like, because people don't usually end up enjoying things that they're really bad at. It's
Mhm.
quite rare. Like, do you know anyone who really enjoys singing but is really bad at it? So if they truly weren't connected, you would see that happen, right?
Mhm.
But
Well,
yeah,
I know one person who is very bad at something but still enjoys doing that. And
singing.
no, not singing. It's actually, well, I wouldn't. It's just
Uh,
silly joke. I meant myself, like
uh.
speaking English. I know that I'm very bad at English, and like I make mistakes, and
You're pretty decent at it though.
yeah, but
Well,
I see some improvement. But for the first,
yeah.
for example, now it's I feel very content with that. But few years ago, 3 years ago, when I just started, it was so there. I felt anytime when I recorded videos, like you may watch my videos, like I recorded at 1017 or 1018. I can't speak, but I struggle. No, I have to like 10 minutes. I have to say something, and yeah, it took me a couple of years, 3 years. I hated, well, not hated, but I had very, like, there was two types of emotions. So like I felt terrible, but on a kind of logical level, I felt great, since I was, wow, this, I have to do that. It does make me feel good, but I know that it will lead to the point where I will feel good eventually when I learn language.
Yeah, it's kind of like working out at the gym, right? Like working out
Yeah,
when
yeah,
you
yeah,
exercise,
yeah.
it's painful, but then you feel good after. Yeah.
Yeah, but still, like in gym, it's still not the same. For I also do some physical work, and you still enjoy it. It's difficult, but then you've done it, and you enjoy it almost immediately. But here, you know that payoff will come only after like 5 years,
It
or
takes a long time for
yeah,
the
and
payoff.
there's
Yeah.
no much enjoyment, but you're still doing it, and kind of you just enjoy that you may overcome this feeling, which basically tells you don't do that. It's hard, but and you, okay, I do that. It's hard. I overcome it, and kind of it's like self. I guess it comes to the idea of temperance, like this virtue of temperance, self-control, and the ability to pursue the rational path and not be overwhelmed by your emotions, like
Mm.
this emotional control by applying your rational thinking.
Takes a lot of discipline. Like you
Yeah, yeah,
know what's
yes,
right and you gotta do it even if you don't like it in the
yeah,
short
yeah,
term.
yeah,
Yeah.
exactly, exactly.
Interesting.
All
You have
right,
any
so
last questions for today?
yeah, I'd like to ask some personal questions actually.
Mhm.
So So, like, actually, we discussed it already. So there's some question like, how does math affect your life? But I
Mhm.
guess you already said that it makes you feel, smarter, and
Yeah,
it's
I feel like that's the main thing. It doesn't help me do my job very much.
uh
Um, I think it helped me. It made college very easy for me.
uh
So a lot of people in college, they were very stressed about their exams. I took like mostly math courses. And so for me, it kind of made it really easy. And so in college, I was kind of lazy and didn't do too much. But now as an adult, I do it for fun. It makes me feel smart. And I like doing my YouTube channel, meeting with people around the world. But yeah, I feel like when I was younger, I used to be a little more like arrogant about math. Like I used to, I used to think that everybody should do math, and that um, like I used to be kind of upset at people that didn't do math, and I used to think like everybody should do it, and that like math was the best thing you could do or would lead to the most progress in the world. And like I was kind of arrogant about it, but now that I'm an adult, I feel like my views have changed a lot. Now I just kind of see it as something I enjoy, I do for fun, just like anything, like how some people dance or some people like to go to the movies. I just see it as a hobby
So
now that I'm older.
you became more tolerant
Yeah, I
towards
became
people
more
who.
tolerant. Yeah.
Okay, okay. You
Yeah.
mentioned that this movie, Fermat's Last Theorem, it inspired
Mhm.
you, but were there some other figures, for like historical figures, who inspired you, like, to study math? Some other
Yeah.
guys, probably
Um,
some stories, perhaps.
Probably not a lot. So that was the only video I really saw when I was really young. But I guess like what I would do is there was like this international math competition that would happen every year, right?
Uh-huh.
It still happens every year, and like all the countries compete in it, and you can see like the U.S. Usually ranks either first or second. China's usually like first, then the US, then Russia. Um, but just like watching. So I went to a few like summer math programs, and like a lot of the people that placed top in the like world in these contests went there. And like often I would look at them, they were like an idol to me. Like they were like someone I would like worship, like, oh man, I wish I could become like them someday. I never got quite that good, but maybe they kind of made me more interested in it. Yeah.
Have you thought about making kind of you're making this YouTube channel where you just when you solve some problems, right? When you work on the solution with other people. Have you thought about making kind of more theoretical channel, like discussing math with people, something that we're doing now, but you know, do some interviews with professional mathematicians and ask some how they solve their problems and basically learning through this experience of making videos, making conversations. Like, have you thought about doing that?
Yeah. It's really interesting because rarely, I mean, my whole life, I've never been a very extroverted person, right? Rarely would I ever start a group to do something. Usually I wait for someone else to start the group, and then I'll join it. But I felt like this was one thing that I could do really well. Really, I wanted to see, actually the whole channel was kind of an attempt by me to try to become more extroverted, or to try to, I said I always follow other people and I always wait to see what they do, and then I follow along with them. I said, what if I could start my own thing? And that's kind of how it all started. And when I first began, I didn't do a Zoom session with other people. So I just did it myself. I would create my own video. I would put it up and I would see if any people watched it and commented on it and whatever. And it was only once I got enough followers that I decided to do the Zoom meetings. Because before then I wouldn't have enough people to do it. But it was very satisfying for me because it made me feel like I can start my own thing. I don't need someone else to start it for me. So that was a turning point for me.
But do you think about making like what I suggested, something like that? So making conversation, not just solving problems, but having discussions with mathematicians. And
yeah, I think that might be cool, like a Zoom meeting with like other mathematicians where I just talk to them about their experiences.
Yeah, just asking questions, maybe sharing your experience, maybe trying not just solve problem. Like since for me as somebody who doesn't really doesn't into this like geometry, I can watch 1-2 year videos, but then like it's very hard. I can't follow. But if you just talk to people about geometry, discuss some some ideas and try to kind of bring it to the general public, it's something that will probably help you to develop your channel in a more kind of in a way that other people, like there will be people who would like to learn more about theory and listen people talking about math and not just solving problems, right?
Interesting. That's a great idea. I'm glad you brought it up. I'll have to think about that.
Some kind of math discussions, math podcast. Like we have lots of just talks about science, philosophy, and I guess I haven't even seen anything like math podcast, like when people just different guests talking about math and sharing their experience.
Yeah, I just have like a Zoom meeting. I just record me discussing math with like other professors or people that do it, and just their experience of it. I like that idea. Yeah.
Since now it's so easy to find all these people. You just go on it, like type some,
But I know a couple of them because like I went to like a summer math program, and like there were professors that taught at those programs. And then I have a lot of friends that went to that program and now are like professors. So there's like a couple people that I could start with that I know, and then maybe I could maybe
Yeah.
take it to people that I don't know yet. But
Yeah.
yeah,
Okay.
it's interesting.
Okay, Michael, thank you too much for a conversation. I really appreciate that you joined me today. I guess we may stop recording here.
Thanks.